All right, so hopefully the sound is working. All right, so let's look at week 7 homework 1 section 5 question, and let me remember what the problem was. So 5, okay, so there's a mistake in this sentence. It's not 5 200-pound weights, but 5 different weights, 500, 400, 300, 200, and 100 pound. The cable, okay, so that question, sorry, the sentence, the writing in the question is somewhat, I guess I copied from somewhere. But anyway, so what's going on is there are 5 weights, all different weight, and we are basically trying to figure out what form that the cable is going to take given this 0.1, 0.2, 0.3, right? So the problem is clear. All right. Then let's see. So let's do that. Alright, so let me not show this. Alright, so first of all, so we have these 5 weights, 500, 400, 300, 200, 100 pounds, hanging at equal distance from, in X direction. So it's 0.1, 2 support points, 0.1 and 0.2 are 10 feet apart, and all of these are 1, 2, 3, 4, 5, 6. So 6 equally spaced intervals, and then at these 5 points there are 5 different weights hanging down. So that's fine. So we'll translate this to a loading diagram, which is here. So right now we don't know, well, we don't really need these reactions for the cable problem. We will for the beam problem, which I will show you later. But the loading diagram, basically you would put these 5 points at equal spacing. So we'll just map all of these 500, 400, 300, 200, 100, and make sure that they are to scale. So 50 inches representing 500 pounds. That means basically 1 inch represents 10 pounds. So this diagram is okay, right? So you just translate this to loading diagram, and then we would name all of these areas between the forces. So A, B, C, D, E, F on the top, you go over these 2 endpoints, and the bottom part is G. So let me even do this part 2. So the way to construct the force diagram is by starting here. So let me. So on the left side we were looking at the loading diagram, and we're gonna construct the force diagram on the right. So here, this one, which is 500 pound, is between A and B, so I'm gonna call the start point of the first force A. The end point should be B. It's technicality, but they should be uppercase just to differentiate between the loading diagram and force diagram. And then next you're gonna map the 400 pound, and since this is between B and C, it has to start from point B, which is right here, and it's on the left you have B, on the right you have C, so the end point of that force on the force diagram would be C. Alright, so that's the second one. The third one is right here, 300. So you're gonna copy again this, because this is between C and D, C on the left and D on the right, so that means C would be its start point and D would be its end point. again call that D. Let me hide. I'm gonna hide this too. And you basically keep going. So D 1, 2, 3. That's the third one. 1, 2, 3. The fourth one is DE. So starts at D, ends at E. Next one is 100. Starts from E, ends at F. So again, we know the height difference between point 1 and point 2, but we kind of have to start from the arbitrary point on the right and draw the temporary diagram and then adjust that diagram. So I'm gonna arbitrarily locate this temporary point P on the right side and connect it to point A, B, C, D, E, and F. So you get these 5. No, how many? 1, 2, 3, 4, 5, 6 lines. So from this, whatever shape it takes, so wherever you put the point P, it doesn't really matter. We would start drawing this temporary force polygon or the form diagram. And you get some kind of a diagram here. So what this is again, it is a funicular curve with this given load, but it's arbitrary point. So it's basically like if you arbitrarily picked the two end support points, you know, it's gonna take, so whenever whatever point you take on the right side and left side, it always takes a funicular shape. Of course, each time it's different, right? If the height is different. So this is true for certain points, which is different from what we want. So let me get the closing point. So in a way, this is true for example, okay, let's say we have 6 feet here, and so this is still a true funicular form, but on a different condition, meaning that all the weights are the same, but the heights on the left and right is different, which, you know, this is clearly different from what we are looking for, so that's why we need to adjust it. So first we drew this closing curve, which I should color code as the same thing as G. So this will determine where point G is on the force diagram. So after, so I started here, right? So after doing this force diagram, I was able to get this curve. Then on the left side, on this force polygon, I would draw this closing curve to make this a closed polygon. Then I would copy this closing line to a temporary point P, which would help us to determine the location of point G on the force diagram, which corresponds to this G on the loading diagram, which is between these two. So this curve is parallel to that one, and the intersection between that line from point P and this vertical line would determine where the point G is. So that's what we get from all of this process, and next step is to basically modify the force diagram and the force polygon so that modify the force diagram so that the force polygon matches what we want to draw here. So what's fixed here is these 3 points, right? So which basically determines the angle of that closing line, which is basically this guy, and the angle of the first segment, right? So what I want to do is, so basically when you modify something, if all the forces are staying the same, you can modify by, right, if the angle, for example, if the angle of this purple line is going to change, it can change, but everything else changes with it. So it's almost like if you move this point P somewhere that matches the condition, and then everything else moves with it. So what's going to happen is we know 2 conditions that we need. So from here we need this closing line, which corresponds to the area G. That needs to change from this to this. We also know this purple line, which corresponds to the area A. That needs to change from this to this. So basically we need to figure out where this point P needs to move so that this yellow line and purple line satisfies both of those conditions. So that's how. So maybe let me change these to like dashed lines so we see the difference. So first I'm going to move this closing line to and attach that to point G, because what we know is we're moving point P, right? But that line is always going to be a line that connects point P and point G on the left side, and none of these points are moving on the left because these conditions are not changing, that the given load is not changing. So that's first condition. Second condition is we know that also where this purple line needs to change to, which is, so this needs to change to that. So basically that means we want this to change to a different angle, which is this one. So that's why I'm gonna again anchor this new A line to point A. And if you scale, I kind of need to scale that big enough. So again, another thing I know is that this line is always going to pass through point A as well as point P. So now we've used these 2 lines. So this line passes through point G and point P, and this line passes through point A and point P. So then automatically we know that intersection between these 2 is going to be the new point P. So I'm going to call this P. So basically we need to modify the whole force diagram. We're going to move the point P from temporary point to the actual location that we just determined. So that's basically our new force diagram. And if you drew the fourth polygon based on this diagram, you should get the funicular form that matches the condition that we are defining on the left side. So you basically connect A, B, C, D, E, and F. So to demonstrate, so to put that in context, if I copy all of that, 0.1, 0.3, 0.2, and these distances, can copy it down here. If you copy this geometry to the left side, it matches these height differences that we set. So this is basically the shape of the cable that is going to take, given this different height, 0.1 and 0.2, and then all of these forces. So basically that's 500, 400, and 100 is here. So that's kind of what it's doing. Guess I didn't put it there, but I think one thing you can notice here is that because the weight, right, the magnitude, I don't think I have to demonstrate. Should have brought more weights. But the fact that it's 500 from the left side and it gets gradually lighter, right? That's why this curve it's deeper here, and it's not sagging as much on the right side. If it's all same weight, like 100 everywhere, then I mean, we could draw it. Maybe that would be a good kind of practice, but you know, that would end up looking pretty similar, but you know, it's going to be much shallower than, you know what I mean? Like, you know, this weight is much heavier, so that point is being sagged down deeper than other points, which was kind of what I was trying to demonstrate here, but I only have like 1, 2, 3, 4, 5 weights, so that doesn't really work. So maybe I'll show that next week. But you know what I mean, right? All right. Yeah.
I missed the point. How did you draw the opposite arrow? How do you know how long you have to draw?
These guys?
Yes.
That's what we are going to cover today. So let's move on to the next problem, but that has to do with this closing line. So for this, so this is really an intro to a beam problem. So the only thing so I'm actually kind of lying here for all of these problems. There's one thing that is kind of technically wrong, but I didn't want to, I mean, this was more for, but I didn't want to get into it yet. But what's happening here, if you imagine, anyway, So what's happening here is like I drew these two, like, so these would be reactions, so that would be a force at each support point. But I lied a little bit, because if you imagine, it's actually best demonstrated with compression only structure, but if you imagine a cable, right, like this. So let's imagine this is a cable that's hanging between, let's imagine like two walls, right? And then you have like a hook on the wall, and then you hook the cable onto that, and you're hanging the cable, hanging the chain like this. The force at this point, for example, that point is actually that much, and this is in tension. So, and you can actually get the exact, actually, didn't we do that somewhere? We identify the internal forces everywhere. Okay, so for example, we have 269 pounds, 269 pounds in this cable. So that's tension in this cable, right? So that means actually on each point, each end point, right? This cable must be pulling a, I'm gonna draw it smaller than it is because it's just a diagram, conceptual diagram, but there's gotta be a, so what's happening here is this cable is fixed at this point and it's pulling that point, right? And then there's also a weight here, I guess. The weight is hanging down. Let me, so that's kind of what's going on. I mean, this scale is kind of wrong. So if I need to show it to scale, right, so don't worry too much about what I'm doing right now. Let's forget about this number, but let's imagine there's this simple cable here and it's hanging, and these two, so it's, let's say it's hanging from the wall, right? So the cable is attached to the wall somehow, it's hanging down, that much weight is hanging here. So if you take each of these points, right? So for this point, there's a downward force, which is obviously the applied weight. And then this cable is pulling this way, and that cable is pulling that way. And you know from the very beginning of the semester how we added the forces using vector mass, and if the point is in equilibrium, in other words, if this point is not moving, then all the forces should be balancing, right? So all these three forces, if you add all of these three forces, it becomes zero. So it's in equilibrium. So that means, you know, this cable is in tension, cable is in tension, and the weight is hanging here. So if you take this cable, because it's in tension, right? I'm trying to pull two ends, right? So it's pulling that point, but it's also pulling this point. So if you, and if there's nothing else working at this point, then the cable should just kind of like fly off from the wall, right? So, but if it's attached to the wall, so the wall has to be doing something. So what the wall is doing is actually, it's pulling this point back, right, through a hook or whatever that's on the wall. And the same thing is happening here. So in other words, the reaction at that support point is actually this diagonal force, which actually have a vertical component, right? So this can be decomposed into two components. So some people could also argue that yes, of course, it's supporting that point vertically against the gravity, but also pulling perpendicular to the wall. So you could say that's the force that's acting there, but also you can add these two forces and say, you know, simply just say that. So in that sense, what I'm kind of lying in all of these diagrams are the way I'm showing these reactions, right? Because I'm only showing these vertical components, but it really actually contained. So in this case, the reaction at that point was actually here. Like, I mean, it could be this way or that way, depending on how the force is applied. But that's the real reaction in this case for the hanging cable. But I was just showing the vertical component, which is actually matches the vertical component of that diagonal force. But that was just so that it's easier to draw this diagram, right, going this way, and also it wasn't really necessary to make that differentiation for this particular problem. But that's why it was kind of a precursor to the beam problem, because what we are going to be looking at next is the beam, which is so this is the new file, sorry, so it's the week 8 beam 1 file. But so what we will be looking at is a beam. So you know, everyone knows what the beam is, right? So beam is like this sort of a long, slender stick type member that has columns on its as its support. You know, sometimes it has columns in multiple locations, but we will start by looking at this simply supported beam, basically this straight member that's supported at two ends by these columns, right? So in that case, it's different from the cable that's hanging from the wall. You can only have these two vertical reactions, and yeah, so that's how we are going to show the reactions at the beam. So the different thing between, so I'll get into the beam more deeply after we do these problems, probably next Wednesday or Monday. But cable, the way the cable resisted loading was just purely through its axial force. Axial force meaning the force that's basically parallel to its own length. So because we've always been looking at the straight, sort of long, slender, straight members, right? For the cables, the only force that's in each segment of this cable is in the same direction as this line of the cable. So in other words, we're not within this cable, we are not assuming any force that's perpendicular to it or anything like that, right? So there is no force like this in the cable. The force is always in the direction of this cable. But for the beams, beam basically resists. So I mean, unfortunately, these are not the beams. But if you go to like the new architecture school building or any beam, right? Yeah, good. So typically you see these, that's a good one. But yeah, you have, so the red ones, these are the beams. You have the beams, you have the columns supporting the beam, and on top of the beam you have the floor, right? So the beam is somehow, it's always resisting the load from above. Typically it's a floor load, and it's being supported by these two vertical columns. And the way the beam resists the loading is through bending, right? So what happens if you, so with the cable, if you hang these weights, it's just kind of like sagged down and it took these straight lines. And if you made the weight heavier and heavier, it just sagged down deeper, right? So that's what happens to the cable when you introduce some load. What happens to the beam when you introduce a load. Typically in the buildings you don't ever see the beams bending, right? Because if you see that, that's probably a problem. But if you for example take like a one by one stick and you put it between like these two concrete blocks or something, and you try to stand up on top of it. Eventually, if maybe you'll be okay with your own, but like the more people get on top of it, the beam, the piece of wood starts bending down, and eventually it's gonna snap, right? So that's that phenomena of bending is precisely how these are resisting this vertical load. How that works internally, I would go through that in the next lecture. But you kind of get it, right? Like that's how it's basically resisting the gravity. Anyway, so first of all, okay, so then we talked about then let's talk about these reactions. So reactions are basically, if you have, so let's say you have a beam here, and just for the sake of the argument, we're gonna ignore the weight of the beam itself, right? I mean, that's actually never the case in the physical world, but for the sake of analysis, we gonna pretend that this beam has no weight whatsoever. Then we're going to introduce these two loads. I'm calling it as 10,000 pound and 5,000 pound. And the force scale being, that's a little bit weird force scale, but I'm using 20 inches line to represent 10,000 pound force. Whatever. So I introduced these two forces, right? There's gotta be, and then I'm saying there will be a column on each end. So this is again called simply supported beam. If you have these two supports at two ends, that's called simply supported beam. So if I say simply supported beam, this is basically what you assume. But anyway, so we're gonna have these two columns supporting this beam. There's gotta be some kind of upward force in the column that's pushing the beam up. Otherwise, this beam is just gonna move down, right? But it's not doing that because it's being supported by the column. So it's the same thing as this table, right? I can press it down, but it's not sinking to the ground because these two actually four legs are supporting on two ends. So just by looking at this, right, you can kind of tell that. So if this was just one load, right, in the middle, then it's, before we do any calculation or anything, it's pretty obvious that reactions in these two columns must be two equal, half and half on both sides, right? Because all the forces, all the vertical forces should be resisted by the opposite force. So that's another thing. All of the downward force, for all of the downward force, there should the total of R1 or R2 should always be equal to the total of all of these applied force. So for this, it would be really easy because the two, actually I want to put this in a different color, but it would be, for each, it would be just half of that. Right, just making sure that these two are the same lengths. But reaction 1 and reaction 2 would be exactly the same. So if you add this and this, it should be equal and opposite of that. But because it's not symmetrical, right? It's 10K here, 5K here. So let's just change the color actually. That's 10K and 5K, and it's not symmetrical, so we don't really know what these two needs to be. But we know the addition of R1 and R2 should be 15. So these two are just for now shown diagrammatically, and they're not correct. But anyway, so that's what we are gonna try to analyze now. So the process to analyze these is actually exactly the same as when you drew that funicular curve. And since this is a beam, you already have this loading diagram. So all you need to do now is actually start this process of labeling these zones again. So you have A, B, you have C, and you have D here. So that's how you start the diagram. And then again, we are going to start the force diagram on the right side by connecting. So this is this one, 10K, and then you're gonna also copy this 5K. Right, so you have this diagram, and again, I'm gonna draw a random point P. So it's almost as if you were to look for the form of that cable for this. You need these lines of action. So this is a fairly simple diagram, so you can start this from here, extend. Actually, let me copy this to the edge too. And B is here. And C is here. Again, what really matters is this closing line, which D is again between this reaction 1 and reaction 2. So let me just put the colors so that you can see. This is, each of these are this color, and closing line which corresponds to this D. So what you realize is you have point A, right, point B, and point C on the force diagram, but we don't have point D because we didn't really know where it would be. But now you have drawn this closing line, we know this where this point D is, which is going to be here. Basically, if you anchor this closing line to the point P, and if you get the intersection between this vertical line and this diagonal line, that's going to be point D. So that's basically what defines the location of point D. Again, also that basically determines the magnitude of these two forces. So these two are placeholders, so I'm going to close them. But now that we have point D here, so if you connect C and D, the force here is between C and D because you always kind of go around. So you go from C to D. So what connects point C and D, so it needs to start from C and end at D, and arrowhead would be then on the D side. So that would be a reaction on this side. And the next reaction on the left side would be A, because it's going from D around an A. So if you connect from point D to point A, that is the reaction on the left side. So what's important is, again, because it went down from point A and came back to point A, right? So the addition of these two upward force, so if you add R2 and R1, that's basically equal to adding 10K and 5K. So the total lengths of these guys should be exactly the same. But they're differently distributed, so in order to identify the scale of these guys, the magnitude of these guys, you would so again, the force scale was 20 inches, 1 inch equal 500 pounds. It's a little bit hard to calculate, but if you get the lengths here, it's 13.33. I'm gonna cheat a little bit, so it's basically 0.5 K for 1 inch, and it was 13.3333, so it's basically 6.66 K. And then the other one is 16.66 inches times 0.5, it's 8.33. So you see how on this beam there are two loads, but one's heavier than the other, so that the vertical force in these columns are different on the left side and the right side because of the way it's distributed. That makes sense? Right. So that would be kind of a lot of what we will be doing. But this diagram will be important in terms of identifying the reaction, as well as other things that's called moment diagram, which I'm again going to explain what that means, and also that's why we wanted to cover the concept of moment first last time. But all you need to know about moment is it has to do with the force and the distance, and it talks about the tendency of a force to rotate an object. And it's the product between the force and the distance, and so the unit is always some sort of a variation of inch, like pound times inch or something like that, pound times force, foot or something like that. But anyway, so does this part make sense? The reactions, right? Vertical reactions. You guys are very quiet. So why don't you take these two examples? So one is same exact weight moved to the left 10 inches. The other one's moved to the right 10 inches. But same exact condition otherwise. But the reactions, so you can imagine how it's already. So if you compare these two, right? So if you look at the loading, I mean, it's equally spaced out, right? So it's equally spaced, but left one is slightly heavier. So it kind of makes sense that, whoops. So it kind of makes sense that because this is heavier on the left side, it kind of makes sense that this side got heavier because you have more load on that side, right? I guess on this. So if I were to guess, right, if you move these two forces, like same forces, to the left side a little bit, you know, your guess is that R1 should get even bigger than 8.33 and R2 should get smaller than 6.66. This third one is different, right? You're moving it to the right, so it should, the R1 should get smaller than 8.33 and R2 should get bigger than 6.66. So why don't we do the second one first, moving it to the left. And let's wait till 10. But again, it's the same exact process, so okay, so I'm looking at this explanation. So this is how I'm starting the force diagram. So typically you start from left to right, and so first I copied this one to here, right? The second one is this one, but also the way to make a connection between this diagram and that diagram is that this one is between A and B, right? And we kind of always follow this loosely, not loosely, but you always kind of follow the clockwise order to name these forces. So basically all the forces are acting as a boundary as well as the beam itself. So those are the boundaries. So anyway, so that force is called AB, and because I'm gonna call it AB, it's somewhat arbitrary, but that's the rule that we are following. On the force diagram, I want to call that force AB2, and the way to label it that way is always to start from point A and end at point B. So these basically corresponds to the left one and the right one. So that's how you know the relationship between these two. So the same thing for the second force, which is on the left you have B, on the right you have C. So I'm going to call this BC, and I want to call the same force on the force diagram BC2, and it always starts from point B and ends at point C. Does that make sense? Yeah, cool. It's not too fast, but I'll try to not move around too much on the screen. So the same exact process. So you basically start by copying these forces. Well, first you start by labeling these areas. So it would be A, it's called A, B, C, and D at the bottom. These lines are slightly confusing, but so that you know that it's between this R1 and R2. Anyway, so the first one is called AB. I'm gonna put it to the side, and it's gonna start from A, ends at B. Same thing. BC ends at C. Right? And then I'm gonna place the random point P on the right, and connection between PA, PB, PC, which is gonna correspond to A. A is always gonna go to A. B is always gonna go to that B section. The C is always going to go to C. Then let me just use different color. The closing line is what really matters. So that lines is going to help us determine what the reactions are. and unfortunately it's super close to point B, so I don't want to zoom in too much, but anyway, so I need to first trim this so that we are close by. But anyway, so if I zoom in, that's the intersection point, so that's gonna be basically point D. So it's really close, so it's kind of hard, but anyway, so if I connect from point C to point D, that's going to be the reaction on the right side. So that's, let me pull it to the side. Right, if I connect from point D to point A, that's going to be the second reaction. And again, the combined lengths should be exactly the same because they're in equilibrium. But then so those two are the reactions. So this part that's called CD, that would be the one on the bottom because it's starting from point C and ending at point D. And then the next one, the reaction on the left side would be this one because it's going from D to D to A, and this is going from D to A if you follow that clockwise. So then you get these two as a reaction. So now you can see how, compared to the first one, the left part is now significantly larger than the right side. And if you get the length, that's whatever that length is, so 19.1666 times 0.5, that's 9.58 K. The right side, that's 10.83. So again, if I were to apply that scale, 5.42, that's going to be the reaction on the right side. Again, though, the important thing is if you add these two, it's 15, so it should be always equal to the total of all the downward forces here.
Y times 0.5?
Oh, that's the scale that we are using. So again, as always, we are using a arrow. We are using the vector, or we're using the arrow to represent the force. And the length of that arrow matters because we are basically representing the magnitude of that force by the length of this arrow, right? But the length is in inches, right? And the force is in pound force or any other units, right? So basically, so that's kind of arbitrary and it would always be given, or when you could decide to use certain scale, but in here it just happens that I'm like, that's kind of what I wrote in the beginning, but I'm using, so for scale I'm using, so this one represents 10K, which was given, right? So that happens to be 20 inches line, so I'm using 20 inches to represent 10K or 10,000. So right, so 1 inch equal 500 pound or 0.5 K, right? So yeah. Any other question or yeah?
Sorry, what's the answer for the left arrow?
That's roughly 9.58 K.
Thanks.
Yeah. Did it work? Yeah.
So yeah.
Okay, cool. So that's, I mean, this is pretty sort of like a mechanical process, but I just want you to get familiar with this first. So, but now we are, is it? Yeah, 10:15, right? 10:15 is the end of the class. So, I mean, you can do this. I'm not going to do it right now, but just please get familiar with this process. And here, I have the demonstration, which is kind of like step-by-step written description of how the process works. So another thing here is though, so first we really need to be able to get the reactions. So that's one thing that I'm trying to get you familiar with it. But maybe next week. So whatever we are drawing here, which was the funicular curve, and it was the shape of this hanging cable, or if you flip it, it was the shape of this compression on the arch. And that's why I made you to do that first. But that happens to represent something in the beam as well. And this diagram for the beam, it's called a moment diagram. And so basically, whatever you drew here, so we've already drawn a moment diagram for two beams without necessarily knowing that's what it is. So from here, I'm going to explain what the bending moment is next week or Wednesday. But from here, we can calculate the maximum moment in the beam by basically determining, so whatever this diagram, you always get this maximum height. So the height, if you cut the slice in this diagram through here, you know, like if it's through here, the height would be from here to here. So basically, actually, we can calculate what is called bending moment at any given point of the beam by basically measuring the length at that point, measuring the height of this moment diagram between these two lines at that particular point, and then what you do, I mean, you can read on here, but you can calculate that by basically multiplying this height, which is in inches, with this distance, which is basically the horizontal distance between this vertical line and point P. In this case, so we are going to translate that to force, because this is a force diagram and every single length represents the force. So we're going to use this horizontal force, which we are going to refer them to H force. So we're going to multiply this force and this height, and that's going to give us the moment, bending moment of this beam at any given point. And the important thing again here is the unit for the moment, because we are multiplying the force here, which is in this case kilo-pound force, and this height, which is inch. So the unit for the moment would always be, you know, pound, inch, or any variation of that. But always it's going to have, for the unit, it's always going to have the force part and the length part. It's the force multiplied by length. So yeah, so if you read any regular structure textbook, you are going to be required to calculate this bending moment by doing a lot of multiplications. Basically, like, you know, you take the point and then you measure the distance between that point and this force, and you multiply. You do a lot of calcs, and we tend to lose a lot of students along that way. So it's not super intuitive. It's kind of cumbersome. But here, all you do is you draw this diagram once, and then you get the length, and you get the length here, and then you get the bending moment. So first, I want to basically get you familiar with the process to get the answer fairly intuitively and quickly, and then I'm gonna explain what that means. Next class, I think. But so try here too, maybe. I mean, we only have 3 minutes now, so you guys can go now. But try to read through this, right? So we've already covered up to this point where you get the point D and reactions, right? And I kind of explain what the moment, how to calculate the moment. But try to read through this, and There's also a diagram called shear diagram, which I will explain later too. But really, next week I will try to. Well, maybe we should. So I think we should still try to. I will try to have a couple of more problems to calculate the bending moment. This is Monday, right? Yeah. So after we do a couple of those, then I'm gonna explain what that means, what we're doing here. So hopefully that clarifies everything. But in the meantime, if you have questions, let me know. Otherwise, I'll see you on Wednesday.